Hi, this is Ms. Moser, and welcome to Vectors, an Introduction. So we're going to start to talk about motion in two dimensions now, and up to now, all the types of motion we've talked about have been exclusively either on the x-axis or on the y-axis. We haven't dealt with anything that's moved in two dimensions at one time. And to do that, we're going to have to develop some new skills. And the big skill we're going to have to develop is thinking about motion in component pieces. But first, let's just talk a little bit about scalar and vector quantities. You may have thus far heard the term vector in association with the difference between vector and scalar quantities, because all physical quantities that we can talk about can either be classified as scalar or vector. And a scalar quantity can be completely described with just magnitude and units. So time is a scalar quantity. We can say something happened 12 seconds ago or took 36 seconds to occur. We don't have to say 36 seconds to the north or 36 seconds in the future or 36 seconds in the past. It's all magnitude and units. Vector quantities have a magnitude, units, and some direction. So velocity is a great example of this. We can say that the speed of the vehicle is 32 meters per second, but it doesn't tell us where they're going. For that, we need to specify a direction. So they could be traveling 32 meters per second to the north, or 32 meters per second backwards, or 32 meters per second straight up in the air. Because of the fact that vectors have this directional piece, we tend to keep track of vector quantities graphically. So we tend to draw diagrams that represent the motion of the object. In this case, I've drawn an arrow to represent the velocity of some object, and then I'm going to specify that this is an initial velocity. I'm going to specify that the velocity here is 15.2 meters per second, and I'm specifying this direction. I'll say it's to the east. Okay, because we can track vectors graphically, we can also deal with that problem of two-dimensional motion using graphics. So, let me give you an example. We've been dealing with things like this: velocities to the east, velocities to the south, motion on a single axis. But what if we have motion that's like this? Oh. So suddenly we have a velocity that, we can tell that it's pointing somewhere southeast, but we can't actually identify the direction for this vector quantity. So we know that, maybe this is 13 meters per second, but we need to get a heading on this. And the first and easiest way, maybe easiest, that we're going to learn to do this is using these graphics. So you'll need a ruler and you'll need a protractor after I walk you through some examples. Go grab a ruler and protractor. Here we go. We'll start off getting a heading for this using graphic vector analysis. So we have been told that the velocity here is 22 meters per second, and we can actually use a ruler and create a scale for this, and that makes life a lot easier. So here I'll go ahead and, I could say that I'm using a scale wherein each centimeter is equal to 2 meters per second. So I've drawn an 11 centimeter long line, and that represents my 22 meter per second velocity. Great, so I've established a scale. That's good. It still doesn't help me with the problem of the heading. So let me get rid of this, and this is where the protractor is going to come in. So we use the points of the compass rose. And this is my little compass rose up here. You know that in the Western world, we're pretty accustomed to imposing a Cartesian coordinate system on the four directions. And north is the positive y-axis, east is the positive x-axis, west is the negative west axis, sorry, west is the negative x-axis, and south is the negative y-axis. So what we do when we are looking at a vector like this that doesn't neatly fall into north and south configurations is we put this little imaginary compass rose right at the beginning of our vector diagram. And when we line up that little compass rose, we can then look at, on a protractor, where this vector falls with relationship to the four cardinal directions, or to up and down or left and right. So we're going to start off with the cardinal directions. Well, this vector originates right here, and it comes out and crosses the protractor right there. And if we really zoom in, we would say that that's at 22 degrees. And now I'm counting from a 0 degrees here, 10, 20, and I'm 2 marks past here. So I am at 22 degrees. But 22 degrees where? Just by itself, 22 degrees makes no sense. Well, this is where we start to think about the directions and orienting ourselves. So we started off, going back to our compass rose, in the east. And from the east, we went towards the north. So this vector is actually 22 degrees north of east. And we very often abbreviate those by writing N of E or S of W. This is an important skill. So when we describe this vector, to give a full description and correct description of this velocity, we would say that the velocity of whatever it is, the bird, the duck, the car, the ball, whatever object we're talking about, is 22 meters per second at 22 degrees north of east. I did not intend for those both to be 22, and I couldn't do that again if I tried. So that's how we give a complete description of a vector. Now, what if we want to find motion when we've had a lot of little bits of individual motion? Let's talk very briefly about the idea of a resultant vector. So here we have a case where an individual, that's my little stick person, has gone someplace, and where they've ended up is the result of two distinct components of their motion. So they had displacement number 1, and we'll call this, I don't know, 19 meters. And this displacement was all directly to the east. So this was 19 meters to the east. Then they had displacement number 2, and displacement number 2, it looks like it was about 17 meters. Great. Oh, I should have put my scale in here. Well, I didn't for now. But, you know, to the what? Well, we can get our protractor out, and by doing so, we find that displacement number 2 was however many meters at 40 degrees, and that would be, again, north of east. Okay, great. So we've described the two component pieces of this individual's displacement, but what we really want to know is where they are now. And this red line, and I'm going to get rid of it for a second, because we were just told, well, they walked here, then they walked here, then they walked here. Great. Well, what we really want to know is, where did they end up? What is their final displacement? And to do that, we take these component vectors and we look for what's called their resultant vector. So this would very often be called the resultant displacement. We can have a resultant velocity or a resultant acceleration. The resultant is just simply the sum of two vector quantities. So the cool part about doing this graphically is we can actually, if we draw this very well and draw it to scale, we can figure out the resultant just from the image. So let's go back and let me fix these quantities, because I just sort of pulled numbers out of my hat, and I should have used a ruler, so hold on. Okay, we'll assume that I've got the ruler scaled here, and that 1 centimeter equals 1 meter. So this would then be a displacement of 14.5 meters to the east. Great. Let's look at the displacement for the other portion. And this gives us a displacement using the same scale, and it's really important that we do use the same scale, of 13 meters. And using the protractor, we said this was at 40 degrees north of east, even though I screwed up and wrote N. Alright, so now, what's the resultant displacement? Well, if we've done a good job, then we can actually use the ruler and the protractor to scale. I'll have to do a little bit of fancy footwork here. And we can measure out, we've got 20, now we're just going to move it down. 20, so we've got 30.5 meters, and we can also figure out the heading, because of course 30.5 meters is pointless if you don't know in what direction. So we'll get out our old protractor again. There she is. And we'll line up the start of that vector right on the little dot in the middle of the protractor. And lo and behold, that's at about 19 degrees north of east. So we not only can track vectors graphically, we can actually figure out a resultant vector graphically. That's actually where we'll stop, and there are some practice problems in the book, in the Holt Modern Physics, that you'll find in the first section of the book that you can do a graphical solve for. All right, that's it.